An object so powerful, so dense that nothing, not even light, can escape its grasp. Black holes lurk in the depths of space with an insatiable hunger for anything that comes too close. They are invisible giants, silently bending space and time, swallowing stars and reshaping entire galaxies. Their presence can be felt across the cosmos, including our own Milky Way. Let's journey into the heart of these cosmic monsters, exploring the different types of black holes and their strange properties with real-life examples that defy belief, from the massive black hole at our galaxy's center to the mysterious phantom black holes drifting in space. By the end, you'll see why black holes are some of the most feared and fascinating objects in the universe. The enigmatic stellar black holes, born from dying stars, have a way of capturing our imagination. They were once just theoretical predictions, but over the years, astronomers have uncovered more and more evidence that black holes are very real, and they're scattered throughout our universe. These cosmic giants form when massive stars run out of fuel and collapse under their own gravity, compressing all their matter into a single point known as a singularity. The singularity is a place of infinite density and gravity so intense that all matter is crushed into an unimaginably small space. Around this point lies the event horizon, a boundary where gravity is so strong that not even light can escape. Beyond the event horizon, scientists can only speculate on what truly happens. Some suggest that everything that falls into a black hole is compressed to a single point, crushed to an infinite density at the singularity. Others believe that black holes might be connected to wormholes that lead to other parts of the universe, or even to different universes altogether. All we know is that once something crosses that invisible line, it's beyond our reach. Once anything crosses the event horizon, whether it's a beam of light, a planet, or even a star, it's lost forever. Our best scientific theories, like Einstein's theory of relativity, explain how gravity works on a large scale and predict the formation of black holes. But when it comes to the singularity, these theories start to fall apart. At this level, our understanding of physics breaks down completely, and the usual laws of nature no longer apply. It's as if black holes exist as a kind of wall in our knowledge. Black holes come in various sizes, from stellar black holes a few times more massive than our Sun to supermassive black holes that weigh billions of times more. These supermassive giants sit at the heart of galaxies, shaping the lives of stars and planets around them. Black holes can feed on nearby stars and matter, growing larger and more powerful over time. Stellar black holes, though only one type in the wide spectrum of black holes, are some of the most iconic and well-studied. When a massive star, one with at least 8 times the mass of our Sun, reaches the end of its life, it undergoes a transformation that's as violent as it is final. For millions of years, these stars burn hot and bright, fusing hydrogen into helium and then into heavier elements, with the force of nuclear fusion pushing outward against the force of gravity. But eventually, they reach a point where they can no longer sustain this fusion process. With no more fuel to burn, the outward pressure disappears, and gravity takes over completely. The core collapses inward under its own weight, and in a fraction of a second, it becomes so dense that a black hole is born, and the rest of the star is blown outward in an explosion called a supernova that can briefly outshine entire galaxies. But what's left behind is a darkness so powerful that nothing can escape it. The newly formed black hole may start small, but as it consumes nearby gas, dust, and sometimes even entire stars, it grows, becoming more massive and increasing the size of its event horizon. These stellar black holes vary in size, but they generally contain about 3 to 10 times the mass of our Sun. Even though they are relatively small compared to supermassive black holes, their gravitational pull is still powerful and far-reaching. In some cases, stellar black holes exist alone in space, unnoticed and undetectable without any nearby material to reveal their presence. But in other cases, a stellar black hole has a partner, a nearby star that it orbits. When a black hole and a star orbit each other, the immense gravity of the black hole can start to pull matter off the star. This material spirals inward, forming an accretion disk, a swirling, glowing ring of gas and dust that heats up to extreme temperatures as it approaches the black hole. From a distance, these systems appear as bright X-ray sources, which can be detected by telescopes here on Earth. Observing these X-rays allows scientists to study the black hole's behavior and even estimate its mass. These X-ray binaries, as they're called, are some of the best evidence we have for the existence of stellar black holes. The intense light they produce reveals details about the speed and pattern of the material spiraling inward, which in turn provides insights into the physics of the black hole itself. The intense gravity of a stellar black hole creates a gravitational well in space, bending the paths of nearby objects. A planet orbiting close to a black hole would experience strong gravitational tides, stretching and squeezing as it moved through the uneven gravitational field. If a planet ventured too close, it could be torn apart entirely, its debris spiraling into the black hole in a final violent encounter. Fortunately, such events are rare, and most stellar black holes drift through space far from any potential victims. In some galaxies, stellar black holes are scattered throughout the arms and disks, hidden among billions of stars. Their influence on their galactic neighborhoods may be small, but each one represents the endpoint of a massive star's life, a kind of cosmic gravestone marking where a sun once burned bright. Stellar black holes remain largely the same size as when they formed. This makes them stable, enduring objects that can drift through space unchanged for eons, holding on to the secrets of their formation in the vast expanse of space. Some stellar black holes may even drift alone, completely undetectable. These quiet black holes pose a special challenge to astronomers because without an accretion disk or a partner star, they don't produce any detectable radiation. They are truly invisible, their presence inferred only by their gravitational effects or, in some cases, by the bending of light from distant stars behind them. This phenomenon, known as gravitational lensing, occurs when a black hole passes between us and a distant star, acting like a magnifying glass and distorting the star's light. By observing these distortions, scientists can sometimes infer the presence of a stellar black hole, even if it is otherwise hidden. In some cases, stellar black holes can merge with each other or with neutron stars, creating gravitational waves that ripple across space. These waves, first detected in 2015, have opened up a new way of studying the cosmos, allowing scientists to observe collisions between black holes directly. Each merger is like a seismic event in space, a brief but powerful release of energy that echoes across the universe. These mergers are rare, but when they happen, they offer a unique opportunity to learn about black hole properties such as their mass and spin. Intermediate black holes, the missing links of the universe, sometimes called the missing links of the cosmos, occupy a unique space in the black hole family. These black holes are neither as small as stellar black holes nor as massive as the supermassive black holes that lie at the centers of galaxies. Instead, they sit in between, with masses ranging from hundreds to thousands of times that of our Sun. Despite their predicted existence, finding and studying intermediate black holes has proven to be incredibly challenging. If intermediate black holes do exist, they might act as stepping stones between small stellar black holes and the massive giants that dominate the centers of galaxies. The idea is that over time, smaller black holes could merge or gather enough material to grow into intermediate sizes, which might eventually lead to the formation of supermassive black holes. But if that's the case, why are they so hard to find? Shouldn't the universe be full of these mid-sized black holes, especially in the bustling areas of space where galaxies collide or where many stars are packed together? One of the biggest challenges in finding intermediate black holes is that they are not as active as their larger counterparts. Supermassive black holes often have huge accretion disks of gas and dust swirling around them, emitting vast amounts of light and energy that make them visible even across large distances. But intermediate black holes, especially if they are isolated or in quieter parts of space, might not have enough surrounding material to create this same type of brilliant display. Without an accretion disk or bright X-ray signals, an intermediate black hole would be almost invisible, blending into the background of space and eluding our telescopes. However, there are some indirect ways to detect these elusive objects. One of the primary methods is by looking for gravitational effects. When an intermediate black hole passes near a star or a cloud of gas, its gravity can cause subtle shifts in the objects around it. Astronomers can sometimes spot these disturbances by watching for changes in the orbits of stars or the shape of gas clouds. Another method involves looking for gravitational waves that are produced when black holes merge. If a stellar black hole were to collide with an intermediate black hole, the event would create gravitational waves strong enough to be detected by observatories on Earth. These waves would offer hints about the sizes and locations of intermediate black holes, even if we can't see them directly. Despite the difficulty in detecting them, there have been a few promising candidates for intermediate black holes.